Welcome to Summarize Science. Today, we are looking at some of the most elusive particles in the universe, neutrinos. Usually, neutrinos are thought to travel through space as ghost particles that barely interact with anything. However, researchers are investigating the possibility that neutrinos actually interact with each other in the early universe. If these tiny particles were bumping into each other, it would have delayed their ability to stream freely across space. This delay would leave a distinct fingerprint on the way matter is distributed throughout the cosmos. The study explores two main scenarios, one where neutrinos interact strongly and another where the interaction is more moderate. To find these signals, the paper suggests looking at the Lyman-Alpha forest, which is light from distant galaxies filtered through clouds of hydrogen gas. They also look at 21-centimeter radiation, a radio signal emitted by neutral hydrogen left over from the early universe. By comparing these two different types of signals, researchers can cancel out a lot of the background noise and static that usually makes data messy. Look at this graph showing how these interactions change the lumpiness of the universe's matter. Stronger interactions actually suppress how much matter clusters together on smaller scales. This is a big deal because it helps solve a problem where different measurements of the universe don't quite match up. To gather this data, the researchers looked at the capabilities of upcoming giant telescopes like the Square Kilometre Array and PUMA. PUMA is a proposed array of hundreds of radio dishes designed to map the universe's history. These advanced instruments are incredibly sensitive to the faint signals left behind by neutrinos. The study used complex math called Fisher matrix analysis to predict how well these future telescopes will perform. The findings show that combining data from the cosmic microwave background with these new surveys works wonders. It drastically improves the accuracy of measurements, sometimes by up to 100 times. For example, look at how much tighter these probability bubbles get when multiple surveys are used together. This combined approach allows scientists to distinguish between standard, ghostly neutrinos and those that like to interact. Even if the interactions are very weak, the PUMA telescope might be sensitive enough to detect them. So, why does this matter for the average person? It means we are on the verge of discovering brand new physics that goes beyond our current, standard model. To recap, neutrinos might have interacted with each other in the early universe, changing how galaxies eventually formed. By using both radio waves and optical light from hydrogen, researchers can spot these hidden signals. Future telescopes like PUMA and SKA will be the key to unlocking these cosmic secrets. This could tell us exactly how heavy neutrinos are and how they shaped everything we see. It is a thrilling time for astronomy as we move from just guessing to actually measuring these tiny, ancient effects. Thanks for watching Summarize Science and stay curious about the mysteries of the cosmos.